Okay, welcome to Astronomy on Tap, Davis. I'm Stefano. I'm a professor at the UC Davis in the physics department. With me is Victoria. She's a graduate student in the physics department. For the people that don't know about Astronomy on Tap, these are a short talk for not astronomer. And in the meantime, when we do the talk, after the talk, we also do some game and other stuff that Victoria will explain. Please, Victoria.
All right, so I'm just going to go through the schedule really quickly so you guys know what we're doing. The first talk will be by my friend, Imran Hasan, who's going to talk about aliens. Yeah, exactly. It's called, Hello, is anyone out there making first contact with civilizations beyond Earth? If you want to ask a question, you can text this phone number up here, 740-278-7699, and we'll put up some signs that say that so you don't forget it. And if I choose your question, you can go to the prize table in the back and pick up a prize, which are stickers and pencils and things like that. Then Stefano and I will tell you about some of the news that's happened in the last month. And there will be a 20-minute break after that in which you can participate in trivia based on the news, which you can also pick up at the prize table. You can win a TMT mug, a 30-meter telescope mug, or a Chewbacca mask for the trivia. And you can also participate in the raffle, and this is where we beg for money. So this is just Stefano and I doing this. We're funding this from scratch, so we need money for some of the sound equipment and stuff. So if you want to donate to the raffle, you can choose whether you think a neutrino from a blazar is cooler, or a neutrino from supernova 1970.
There is no story here. For sure, the neutrino for supernova is the best.
Yeah. We'll figure it out later. And the winner of whoever has the most raffle tickets in there, we'll choose one of the raffle tickets from the bucket that has the most, and the winner will win a Galileoscope. After that, Chris Fassnacht will talk. He's a professor at UC Davis, and he's going to talk to us about dark matter. So we have two of the coolest topics today, aliens and dark matter. His talk is called Dark Matter Through the Looking Glass, and we'll handle questions the same way. And then we'll leave. Yeah, so first up we have Imran.
So I've certainly wondered myself, is there anybody else that could be out there? And I think that's a question that a lot of people ask themselves from time to time, and certainly smart people have pondered. But the cool thing is we've actually made attempts to try to make contact with anybody out there who could be listening, and I want to tell you about those tonight in our talk. So there's basically two ways you could go about doing this, and we'll discuss different cases of both of them. But the first, which you're seeing illustrated in this highly technical diagram over here, is basically to send a signal encoded in a radio message, shoot it into outer space, and if anybody's out there on the other line, they can decrypt it and understand our message that way. And the other way is similar to sending snail mail. So basically you take a physical copy of your message, strap it onto some spacefaring device, shoot it out into the solar system into the great beyond, and hope that somewhere along the lines it encounters somebody who could be interested. But maybe we're getting a little bit too ahead of ourselves. There's another question that maybe precedes this one, namely, how do you know anybody's out there who could be listening in the first place? It behooves us to ask this question because it's not really worthwhile to, send messages into the great beyond if we don't think there's anybody out there to begin with. But there's good news. We can calculate roughly what the chances are of making first contact with other civilizations. And so to do that, we use something that I'm showing you over here, which is called the Drake equation. So basically, this n over here is telling you the number of other civilizations that could be listening, and all those horrible variables in there are basically parameterizing what we think the chances are of different things being true that must happen in order for the signal to get through. So math is very elegant and it's very powerful, but sometimes it's not the most, nicest way, most intuitive way to think about things. So I often like to think about things in emojis because they're intuitive by construction. So the first term and the Drake equation means how many stars are out there. And that makes sense, right? As far as we know, you need to be in the neighborhood of a star to be alive. The second term says, of those stars, how many of those could be hosting planets? And then the next one is, of those planets, how many of those have the potential to host life, how many of those actually do host life, how many host intelligent life, because we want to have a conversation, right? And after that, how many of them can send and receive signals, and finally, how many of them actually stick around. So we have to actually understand that even though civilizations may come to fruition, they could also destroy themselves by annihilating each other in a nuclear holocaust or destroying their environment, things that never could possibly happen here on Earth. Thanks. So the thing is, about half of these parameters we understand pretty well, and we know the numbers for them. We have a good handle on how many stars there are, how many planets there are, and we're now beginning to understand how many planets are in environments that are similar to the Earth. But unfortunately, there's still some information that's left on the table, so to speak, that we don't know well yet. And so we can't get a number to tell us what n is. We don't know exactly how many civilizations there are, but we can set some bounds, basically, and determine the result of the Drake equation with a pessimistic case by using pessimistic numbers and an optimistic case by using optimistic numbers. So I want you all to appreciate this great pun over here. This is the Drake result. And over here you can see Sad Drake is thinking about the pessimistic case, in which case there's far fewer than even one civilizations in our galaxy, but all the way on the opposite end, there's millions of civilizations in our galaxy. And I think they're both pretty interesting. So if you start to think about the pessimistic case, by all accounts, we shouldn't be around, right? I shouldn't be here telling you that we shouldn't be around because it just looks so pessimistic. And yet we are. So maybe this means that we're just a statistical fluctuation. The other hand is also interesting too, because it means that potentially there's millions and millions of other people out there who we could start a conversation with. We could have pen pals on other planets after all. So because I'm supposed to give you a talk that lasts about 15 minutes, we're going to go over here with the optimistic case and press forward. So now we discussed briefly that there's kind of two flavors of sending messages. The first one that we're going to talk about is a radio message. And so first I want to tell you about the messenger. So it comes from an observatory based in Puerto Rico called Arecibo Observatory. You're seeing a picture of it illustrated over here. It's a satellite dish, and it's about 1,000 feet in diameter. To put that in perspective for you, if you were downtown on 5th Street and you started on A Street and walked all the way to about F Street, that's 1,000 feet. And that's the diameter of this dish that you're seeing over here. Another cool fact is that it sits in a natural depression. And so you're seeing in a photograph that was taken in the 60s when the construction was going underway for this observatory, and where the dish usually sits is right over here, and all they had to do is kind of carve out this natural depression that was already sitting in the earth to make way for the kind of shape of the dish that would go in it. And if there's any James Bond aficionados out there, this is also the setting for the last scene in GoldenEye, where Sean Bean meets his demise, as he always does. So we know the messenger, but where are we sending the message? So our target is this star cluster. It's called the Great Cluster in Hercules, so it's in the constellation Hercules. And although you can't see them all in this picture, there's 300,000 stars that live in this stellar cluster. So all these stars are gravitationally bound to each other, and they live together. And so, additionally, it's worth noting that it's dozens of light years across. And so if we think back to the Drake equation, we want to have numbers on our side. So it kind of makes sense to cast a wide net, right? Since this is such a dense stellar environment, and we send one message, we can sort of hope to check as many boxes as possible in terms of anybody who could be out there receiving our message. So I told you the message and the messenger. Sorry, I told you the messenger and the destination, but I still need to tell you what the message is. And again, this poses a problem, right? We don't know how aliens think or talk, but we need to overcome that boundary one way or another if we want to become pen pals with them. So what we can do is send a message and code it in math. Because no matter where you are or who you are, math is always math, and it always means the same thing. So let's look at the expression that we sent them. It's this message, a bunch of ones and zeros. So it may seem underwhelming at first, But if you count the number of numbers here, you'll realize there's a special number of digits. It's about 1,600. Let me see the real number. The real number of numbers is 1,679 numbers. And that's important because that's what we call a semi-prime number. It's the product of two different prime numbers. So if you're a civilization that's worth your intellectual salt, hopefully you'll realize this and see that it's kind of a clue. And so if you choose to organize these numbers in a grid where the rows are made up by a prime number and the columns are also made up by a prime number, and you let the zeros be off and the ones be on, you can decipher it to make this very intriguing pictograph. And so, you know, in principle, there aren't any colors, but the colors are added there for clarity to distinguish the different messages that are being sent. But we'll go through a couple of the cool ones together. So over here, you can see this double helix pattern. And so it makes sense to send that because as far as we know, life on Earth involves DNA. Maybe that's the case for other civilizations too. And if it is, that'll be kind of an interesting commonality. But if it's not, that's interesting also, and it's certainly worth sending that message. After that, you can see a humble stick figure of a person. So that's giving, this is kind of like an interstellar selfie, right? Before we had the age of cell phones and cameras. This is just to give some intuition of what people look like, who we are, who's sending the message in the first place. This is another sketch of our solar system. So over here, we've got the sun, and marching along, we have the planets, and the number of pixels over there is just meant to roughly illustrate how massive they are. And if you notice, the third one is raised to indicate that it's distinct. So that's where the message is coming from. As you know, Earth is the third planet from the sun. And additionally, there's a sketch of the observatory that the message was sent from. So this is, you know, the first message that was, you know, ever in an honest-to-goodness way sent out in the hopes that somebody would be on the other end of the line. And Arecibo message isn't the only message of its kind. In fact, it's been cloned more or less by a company that you may have heard of called Doritos. And so they had among their fans a competition to see who could come up with the best message, or so to speak, in terms of a movie. And they actually paid money to have another observatory transmit the winner. And so I want to share this really deep and meaningful video that got put together by a fan. So we could kind of untangle what the previous message meant by using math, but I couldn't use all the math in the world to figure out exactly what that means. But maybe you can. Maybe the aliens know. Shrugging right along, we're going to talk about the second case, which is snail mail. And so it will involve a pair of spacefaring missions called the Voyager missions. And so to tell a complete story about this message and how it got sent, we need to understand the kind of backstory of these two space missions. So this next physical message that gets sent out was hitched aboard two different missions, NASA missions called the Voyager missions. And I'm showing you a picture over here of what they look like, just to give you a sense of scale. They're each about the size of a compact car. And the primary mission objective was to take a tour of the solar system. And so around the time they were launched, it was realized that the planets were configured in a really neat configuration where it would be pretty straightforward to do a flyby of all the gas giants. And so these missions could get up close and personal to the different planets in our solar system. We would be able to study them in a detail that previously was never done. And so that's what this is showing over here. Basically, we have the orbits of Jupiter, Saturn, and we're showing the paths that these two Voyager crafts take. And basically, they tour the outer solar system, getting gravity assist along the way, hopping from planet to planet, taking pictures as they go along. And so, although it's a bit of a tangent, I kind of can't help but mention it and show you some of the pictures that the Voyager missions took, because frankly they give us some of the most mind-boggling and absolutely gorgeous takes of the solar system that we've ever seen. And so the top right picture that you're seeing is an approach that Voyager had when it was on its route to Jupiter. And it's really, the thing I love the most about this is that you can see the different bands of the atmosphere of Jupiter. You can see the vortexes that form where the bands meet each other. It's just really a gorgeous planet. And of course we have these awesome illustrations of Saturn, its beautiful rings, and its moons pictured over here, and Neptune, one of the gas giants in our solar system. But more back to the task at hand, we're of course interested in space broadly, but more interested in sending messages to anybody who could be out there listening. So what message was sent? So additionally, Voyager had on board what were referred to as golden records. These were records that could be played, and encoded on them were different sounds and different types of music that were selected, so that anybody who happened upon the craft could pick them up, and accompanying the records were detailed instructions about how to play them and so forth. And so I want to share with you a couple of the sounds that are actually encoded on these golden records. So let's hear some of the greetings in the different languages that are on the golden record.
Ashuli. Shalom.
Bonjour tout le monde. Hello from the children of planet Earth.
So those were just a couple, but there's many, many, many more greetings in many different languages. In addition to that, a selection of different musical pieces were also put on the golden records. If you're interested, you can actually look at NASA's SoundCloud account to listen to all the different bits of music and sounds, and also sounds of Earth that are on this disc. But maybe we should pause here and ask ourselves another question. Has science gone too far? Should we be trying to reach out and make first contact? What if the aliens out there aren't benevolent and interested in becoming pen pals with us? As Stephen Hawking said, to paraphrase, if you are prey in the jungle, you don't announce your presence to the predators. And that's more or less what you would be doing by sending out messages. And I don't know about you guys, but I've seen plenty of alien movies in my time, and they never end well. So what do you think? Did we overstep our bounds? Was it a good thing to do? Well, the fact is, whether we meant to or not, we have been soliciting calls to extraterrestrials ever since we started using radios. Radio waves constantly leak off the surface of the Earth. So anything from a rerun of Friends to a Super Bowl commercial is already echoing out into the cosmos. And so it kind of behooves us to make a purposeful message and direct it in a purposeful way, in a targeted way, that at least makes an attempt at making a friendly greeting. It's a good gesture. And so I'm leaving you here with this quote by Carl Sagan that kind of addresses this pessimistic case. Isn't it a bad idea to try to reach out? And I think he makes a convincing case that all things being considered, we are already reaching out, and we may as well extend a friendly hand. So that brings us to the conclusion of my talk. Thanks for laughing at my jokes. If you've got any questions, I'd be happy to hear about them.
That was awesome. Thank you. I think you win the record for the most questions we've received during a talk, maybe. And I didn't.
Yeah, we didn't put the signs out, so
I
it's.
didn't put the signs out, and I also didn't have time to respond to all of you. So if you asked a question, go get a prize if you want it. A lot of you asked similar things. So the first one I'm going to say is, do you think people will understand what the Arecibo message was saying?
I think it really depends on how intelligent and how curious anybody who's on the receiving end could be. And you could make a case that if they're significantly different than us, then maybe the stick figure doesn't make sense, and maybe the DNA doesn't make sense. But I still think that it was a clever idea to choose mathematics as the base kind of way of communicating this message, because these prime numbers are a really, they're a tantalizing and intriguing kind of hint of intelligence. They're very special numbers, and they have kind of a significance attached to them. So even if you don't understand the pictographs, the fact that there's prime numbers associated with them is itself, I think, an intriguing hint.
The next question is, where is the Voyager now?
So both of the first Voyager mission is officially in interstellar space. It's by all measures has left our solar system, and I think it's on its way to a constellation called Ophiuchus. And in about 20,000 years, it will come within about 2 light years of another star. And that's basically the same for Voyager 2, although it's headed off in a different direction. But in about 20,000 years, it will also come within about 2 light years of another star.
So this is a personal question. If it were you and you had to decide what the message would be to send to another civilization, what would it be?
It would be the dankest meme that I could find.
Do you account for the average time it takes, light year, for one civilization to contact another, and relate to that the time of civilization can survive long enough to try to contact?
So that's a really interesting question, right? The Arecibo message was directed at a star cluster that is by the time it gets to them, it'll be about 25,000 years from now. And if they instantaneously respond to us, that's another 25,000 years for us to get the message back. We may not be around, they may not be around. So that's another obstacle to consider when trying to contact other civilizations. It's a good point.
Okay, I think we're done. Let's thank Imran again. Very nice talk. So Imran will be around for the rest of the night. So if you have a question for him, you can directly talk to him during the break. Let's start with astronomy news. So the first news is about a nice result that was obtained this summer in August. This is a nice video of the supermassive black hole that is in the center of our galaxy. And you can see these are roughly 26 years, and you can see all the stars around the center of the massive black hole that is in our galaxy, just turning around the supermassive black hole. You see this star that is very close, is the closest star to the supermassive black hole. And this clever group of astronomers using the VLT telescope this summer published a paper and about confirming the general relativity. Whenever you have a massive object passing close to a supermassive black hole, you can study gravity. You can try to understand how gravity works. And so what one of the things that you can confirm is that we know that gravity not only bends the path of a massive object passing close to a more massive object, but also can bend light. So Chris will speak about this probably later. But there is also another effect that is called gravitational redshift. If you have a massive object and you have another massive object emitting, going around the supermassive black hole, you have this gravitational redshift. So the light that is coming from the object will be change frequency and will become redder. So what this group of astronomers did, they observed the most close star to the supermassive black hole, orbiting around the supermassive black hole. They observed the orbit takes actually 16 years. So the S2 star, the closest star to our supermassive black hole, is taking 16 years. And they observed the orbit for 26 years. And they were taking spectra from the star in the last 26 years, and when the star went very close to the massive black hole, they saw the star getting redder. And so this is a direct proof of general relativity, and so it's a very cool result.
Awesome. So another big milestone achieved in physics this month was the detection of neutrinos with the IceCube experiment. So IceCube is an experiment located in, any guesses? It's called IceCube. Antarctica, right. So it's basically a giant slab of ice with huge detectors underground. And its job is to detect neutrinos. Basically what a neutrino is it's a massless particle. They're super important to physics. It's almost massless particle that there are a ton of. And what I mean by a ton is that there are basically about 65 billion going through your fingernail at any given second. And even though there are so many of them, they're really hard to detect. And even though they're really hard to detect, what's even harder is finding where they came from, so the direction they came from. But IceCube is doing both of these things. So they're detecting neutrinos and also they're localizing them, figuring out where they came from. This is a particle physics experiment, but we astrophysicists care about it too, because almost every astrophysical phenomenon produces neutrinos. We have detected neutrinos before, but we've had trouble figuring out where they came from. So the sun produces a lot of neutrinos, and we are having trouble figuring out which neutrinos came from the sun and which neutrinos came from elsewhere. And IceCube is basically helping us figure that out. So around today is about the 1-year anniversary of an interesting detection that came from IceCube, where they detected neutrinos, and they alerted the astronomical community that they had done so, which means that they sent a message to all the telescopes on this slide and said, turn your telescopes in this direction, there's going to be something cool. The majority of the telescopes that did this got a very pretty look at something called a blazar, which, number one, we should talk about blazars. They're really cool. They're basically black holes that are in the center of galaxies that are eating everything around them. So there are these really energetic phenomena that have cool disks and these jets that come out from the top and the bottom. But also they produce neutrinos. So the reason this is cool is because we have a neutrino detection from IceCube in Antarctica, and also several observations from telescopes of a blazar that produced the same neutrino, and this is the first time that's ever happened.
Wait 1 second. This is not the first time we detect neutrino for an astronomical source. The first time was in '87 when suddenly several neutrino detectors detected an excess of neutrino, and they say, oh, something cool is happening here. Few hours later, roughly 12 hours later, a new object was discovered in the Large Magellanic Cloud, was supernova 87A, the most important supernova ever, I would say. Here you see the picture of the supernova, the massive star. It was a blue supergiant here, and then as soon after explosion. So it was really cool, and this was the first time we detect a neutrino from an astronomical source.
Okay, you're right. I lied a little bit. That was the first detection of neutrinos. IceCube was not the first detection of neutrinos. But this is way cooler, because this was on purpose. Your 1987A thing was luck. It was basically somebody happened to be looking at the sky at the right time, and they found some neutrinos. So IceCube is way cooler because it has this telescope of networks that it alerts every time it finds a detection of neutrinos. It's very sensitive, and it can localize the source. So it can see sources very far away that are emitting these neutrinos and tell us where they are. And we can look at them with telescopes. So,
Okay, go on.
what do you have to say about that?
Well, I still prefer 87A. It was the first detection neutrino for an astronomical source.
Fine. Okay, so also at the end of August, we have gotten the news that there is definitely for sure water on the moon. The Moon Mineralogy Mapper, I always have trouble saying that because I always want to say Mars Mineralogy Mapper, but that isn't what this is. It's called M3. It detected water on the moon. We have gotten it, forgot to say something. It found the water ice on the poles in craters where it gets to a balmy negative 250 degrees Fahrenheit because the sun doesn't shine there because of the way the moon is tilted. And so we've seen evidence of water on the moon before, but this is the first time that we've seen very conclusive evidence. And every time before, it's been explainable by something else. So every time before, it's been, oh, we see something really reflective. Maybe it's water ice. And that's always explainable by saying, oh, maybe it's just really reflective soil or some other reflective thing. This time they saw the exact signature of absorption of water. So they actually just reanalyzed data from 2009 and saw, so what I'm showing here is in the blue is the signature of what water looks like in a spectrum in a lab if it's just pure water. Black is the signature of what just the moon looks like with no water, so like the side of the moon. And the two red ones here have water, that's where they found the water in the moon on the poles, so that has water and moon stuff. And yes, moon stuff is a technical term. So this is the first time that we've had conclusive evidence of water on the moon.
Okay, this other news is actually an anniversary. So we didn't have any astronomy on tap in August, but I had to speak about this anniversary because it's probably the most important discovery in astronomy that was done last year, at least for me. So in August 2017, the LIGO detector, they detect gravitational waves. They detect gravitational wave from two neutron stars merging. That's pretty cool. That was the first time we detect gravitational wave from neutron star merging. But even cooler was that 2 seconds after the detection, the Fermi satellite detected some high energy photons, gamma ray, exactly 2 seconds after the gravitational wave detection. And few hours later, several astronomers, including me, detect an object that was also coming from the direction of the gravitational waves. So this was the first time we detect at the same time gravitational wave plus electromagnetic signal from a source coming from this event in the sky. So it's pretty cool, like the ice cube detection. This is another proof that astronomy now can be done not only with one messenger, with the electromagnetic signal, but actually now we are able to do astronomy with multi-messenger, with gravitational waves, with neutrino. It's pretty cool.
Okay, so our last news is about Hayabusa 2. And if you were here in July, you heard me talk about this. It's basically a spacecraft that's following an asteroid named Ryugu that's orbiting the sun with Earth. And this team is really good about updating their Twitter feed. And I'm a huge nerd, so I've been following it. And so this month, they have chosen a landing site. Their goal is to find the composition of an asteroid, and they're sending down landers to the surface of this asteroid. And so their primary landing site, if they can make it happen, is L08, which is this magenta square here. This is the last tweet that I saw before Astronomy on Tap started today, and it says, the altitude of the spacecraft is now down to 3 kilometers. At the place where they're controlling the spacecraft, the sky outside is beginning to get brighter. So the spacecraft is getting closer and closer to the asteroid, and they're about to send down some landers. This is a picture of the landers and the casing that they came in. Their main job is they each have a couple of cameras on them, and they're going to move around on the asteroid and take a bunch of pictures in order to send back sort of a comprehensive view of what the surface of the asteroid looks like. And if you were here, you remember me excitedly talking about how the rovers move, because I think it's really fascinating. They're not normal Mars rovers. They don't have wheels or crawlers, because if they did, on this particular asteroid, since the gravity is so small, they would gain too much momentum and sort of fly off into space, which we don't want in this particular situation. So instead, they have these internal weights or motors that help them hop around. And as I was reading the articles that came out closer and closer to time, the size of the hops surprised me. So each time they hop up 15 meters, which is over 4 stories. That's really big. And they spend 15 minutes in the sky. So those are large hops. That's larger than the hops that I thought they would make. So maybe by the time Chris is done talking, we'll have an update on this, because the Twitter feed has been getting updated pretty regularly. But other than that, fingers crossed on this. Okay, so this is our break time. Feel free to participate in trivia and the raffle and beer. We'll see you in 20 minutes.
Test, test.
And then please you hear that? Okay. What? You hear on the slide, but you can also turn to the Okay. It's time to start again. Please sit. I hope you took the last beer. Okay, so our next talk is Chris Fassnacht, that is a professor at UC Davis in the physics department. He's my neighbors in the office, and he's a great professor. I speak with him in Italian. And he will speak about dark matter through the looking glass. Thanks you, Chris.
All right, thank you, Stefano. Thank you, Victoria. So today I'm going to talk to you about dark matter. And as Victoria said, this is very cool, something that really excites me a lot. It's one of the two things that I spend most of my time studying. The other thing is dark energy. So I guess if Darth Vader came up to me and said, I want you to join the dark side, I would say, sure. All right, so let's start out, talk a little bit about what dark matter is, or what we think it is. So when we think of galaxies, or at least when I think of galaxies, this is what I think of. It's a collection of millions or billions of stars, some gas, some dust, all held together by gravity. Here's a beautiful picture of the Andromeda galaxy, the nearest big galaxy to our Milky Way. But in reality, this may not be what a galaxy actually is. It may not be the best description of a galaxy. So, in fact, what was discovered back in the 70s by Vera Rubin, right here, is when she looked at stars and gas on the outskirts of galaxies, this material was moving way, way too fast to be held by the gravity that you would attribute to the stars in the galaxy. So essentially, these things were moving so fast that they should escape from the gravity of the galaxy, but they were not escaping. So what was going on? And she posited that there had to be a lot of extra material in the galaxy that we could not see, that was holding, that the gravity from which was holding those stars and that gas in their elliptical orbits. And we can't see it, so we call it dark matter. And it turns out that if you figure out how much mass there is, how much material there is in these galaxies that's made up of dark matter as opposed to the normal stuff that we know, the stars, the gas, the dust, it turns out that galaxies are actually something like 90% dark matter and 10% the other stuff that we know and love. And so rather than considering galaxies to be something like this, which is what we do, galaxies really should be thought of as huge balls of dark matter that happen to have some stars and gas and dust in the middle. And for whatever reason, astronomers call those huge balls of dark matter halos. I'm not sure where that term halo comes from, but that's what we call them. And so here is a little bit, a cartoon version of what a galaxy actually is, a big ball of dark matter that has some stars, gas, and dust in the middle. This strange-looking gentleman down here, you may have seen him in a talk before. This is Fritz Zwicky, who is a Swiss astronomer who was working in the States in the 30s, and he had a lot of really crazy ideas, and some of them were right. And some of them were right way, way ahead of time. So he was actually the first person to think about dark matter, which he may have called missing matter. He was actually looking at something that was not galaxies, but what we call clusters of galaxies, a group of galaxies that's held together. And Vera Rubin was the one who first really looked at dark matter in galaxies. You'll see Fritz again later in this talk. Okay, I always like this picture, this cartoon of what a galaxy really looks like with dark matter, because it kind of reminds me of this. As I said, Darth Vader, sure, I'm in. Okay, so this didn't work, as we could expect. So here's a more up-to-date version of what we think galaxies look like. They are big balls of dark matter, but they're not just big solid balls of dark matter. made up of sort of a big distribution of dark matter and lots of little dark matter clumps in them. And if this had worked, this movie would have shown you a galaxy like the Milky Way forming, where we look at, this is what we call a dark matter only simulation. We're not going to show the movie. We're not going to show the movie. I can't handle two. My hands are full. So in any case, it shows, you know, if we had dark matter eyes, which I sort of really wish I had, since this is what I study, what it would look like over time as the Milky Way assembled. But in the end, you end up with something like this. And what you see is, for a galaxy like our own, like the Milky Way, in addition to the big ball of dark matter that the Milky Way sits in, there's thousands and thousands of smaller balls of dark matter within that big ball. And we call them, very cleverly, subhalos, because the dark matter, the big ball, is called a halo. And so this is what modern pictures of dark matter of galaxies are. Okay, now there is a problem, although this may be less of a problem than we used to think it is, but there was something that was motivating a lot of research in about galaxies, called the missing satellite problem. And the problem was that the satellites were missing. Okay, no, here's what we expect. So all of the simulations that were done, all the computer models that were made of what galaxies should look like, showed that a galaxy like the Milky Way should have thousands and thousands of these small galaxies there. And one thing in this previous slide, when I looked at it, when I showed this, these two pictures here show two different groups, two competing groups, modeling what a galaxy of the Milky Way should look like. And both of them end up with the same thing, a big ball of dark matter that has thousands of small balls of dark matter in it. And, oops, and, oh, wow, the movie went for half a second. Oh, there. Okay, so the problem was that when people looked for small little galaxies that were orbiting within the big galaxy, something that we call satellite galaxies, we weren't finding thousands and thousands of them. Instead, we were only finding tens of them. And so here are some of the most prominent ones. So the picture on the bottom is the Milky Way, if we could see the whole Milky Way all at once. And down here on the bottom are two little bright blobs, and these are what we call the Magellanic Clouds. These are the two biggest satellite galaxies of the Milky Way. Have any of you ever seen the Magellanic Clouds before? A couple of us, yes. You have to be in the southern hemisphere in order to see them. But if you ever get a chance to go to, say, New Zealand or Australia, it's sort of fun. All right, the Andromeda Galaxy, which is sort of a twin to the Milky Way, also has satellite galaxies, so here's a very bright one here. And it turns out that we can see many more than these, but many more gets us to maybe 50, and 50 is not thousands. So this was a problem. Nowadays, more sophisticated models that some people in this room even work on show us that maybe this isn't quite the problem that we thought about. But one of the possible explanations for why we were missing these satellites that people came up with, and this still leads us down an interesting path of research, is that maybe dark matter is not how we thought it was. So the dark matter models that everyone uses for making their models of how galaxies form in the universe is something that we call cold dark matter. Cold is just a fancy way of saying that the particles of dark matter, if there are particles, move fairly slowly. Okay, I'm going to take a step back just because I should have mentioned this before. So dark matter is something that lots of people study. Astronomers study it. So do lots of particle physicists. Why do particle physicists study dark matter? Because astronomers tell them that there has to be dark matter there. The particle physicists forget about this when they talk to astronomers. They think we just take pretty pictures of galaxies and don't do science. Anyway, I'm not bitter. In any case, here is one of the possible explanations for why we weren't seeing the satellite galaxies, was that dark matter, rather than being cold, was warm. Now, back when I was a grad student, it wasn't cold versus warm, it was cold versus hot. Hot meaning that the dark matter particles moved really fast. And we ruled that out based on observations of the universe. Dark matter was not hot. And so that disappeared for a long time. But suddenly, somewhat recently, the concept of warm dark matter came up. And I guess this is like the Goldilocks thing. Maybe it's too hot. Maybe cold dark matter is too cold. Maybe we need something that's just right, which is warm dark matter. So even though this may not be needed to explain the missing satellite problem, the thing is about dark matter is that we don't really understand what it is. And that's what the particle physicists are trying hard to figure out, and that's what we astronomers are trying hard to figure out as well. And one difference between cold dark matter and warm dark matter is that cold dark matter, so these are two computer models here, side by side. Whoops. Side by side. One on the left is with cold dark matter, and one on the right is with warm dark matter. It's the same galaxy that they've simulated. What hopefully you can see even in the back is that the cold dark matter one has many, many more small subhalos than the warm dark matter one does. And so this discrepancy allows us, those of us who study the sky, to try to learn something about dark matter. Is it warm or is it cold? And the way that we can do that is to try to count up the number of small subhalos that are associated with each big halo. And that's what I do for some of my work. So in order to do this, you need to be able to see dark matter somehow. And this is actually complicated because dark matter is dark, which means that we can't see it the normal ways. But there are clever ways to see it, and that's what I'm going to tell you about next, which is the through the looking glass part of my title. So this is a way to see dark matter, subhalos and galaxies. And this is using something that's called gravitational lensing. And Stefano referred to this a little bit during the trivia section, or in the news section. But here's this guy down here, Einstein. And Einstein, among one of his many, many huge advances they made in physics, is he came up with the theory of general relativity. And in this theory, he pointed out that even though light does not have mass, if it passes by a massive object, its path will get changed as if it had some mass. And so this is a cartoon picture of what could happen. Let's see, there's too many buttons on this thing, and I had a beer before talking. So here we go, the sun is here, light is coming from a star here, it passes by the sun, and because of the gravitational field of the sun, or Einstein would say because of curved space-time, the path gets changed, it comes into the Earth here, and because the light is coming into us from this direction, we see the star over here, not where it actually is. Oops, sorry. But not where it actually is, but in this other position. The French call this a gravitational mirage because it's not actually what we see. And the kind of gravitational lensing that I study is this super cool kind called strong gravitational lensing, where it turns out that if you have a really good alignment, okay, now I need extra hands, you can have light passing around one side of the object and the other side of the object, and instead of one object, you see two objects. And so that's what this cartoon up here is showing. So here's our object, here's our massive object. Our background object is here, and light bends around both sides, and we see light coming in from two directions at the Earth. So we see two mirage images. And here's a more realistic version of this. So you have some really massive object like a galaxy, and it produces two fake images. And here's Zwicky again. Zwicky came up with this idea back in the mid-1930s. He says galaxies should be able to produce more than one image of a background object through gravitational lensing due to this general relativity theory that Einstein had come up with. Mid-1930s, it wasn't until 1979 that we discovered the first gravitational lens. So he was way, way, way ahead of his time, at least on this. Like I said, many of his ideas were completely crackpot, but this one, he was right on. Okay. So here's one way of explaining how gravitational lensing works. This is only one way. I like this way because when I was in college, I was on the cross-country team, and the goal of cross-country is you start out at the start of the race, and you try to get to the end of the race as soon as possible. And light tries to do the same thing. So it wants to take the fastest path, but What Einstein told us is that when it passes through a gravitational field, it gets slowed down because time runs more slowly in the gravitational field. And the stronger the gravitational field is, the slower the light moves. Okay, and the reason why I like this example is this is something that actually happened to me when I was in college. So before one of our cross-country meets, it rained a whole lot. And so as we were running down the path, down the hill, there was a big old puddle right there in the middle. And so all of us had to make this decision in real time. What do we do? Do you run straight through the puddle with all the mud and the water slowing you down? Or do you run around the puddle and add extra distance to your path, slowing you down? And so light does sort of the same thing. It has to decide if it goes straight through the puddle or straight through the galaxy, it gets slowed down because of the gravitational effect. If it goes around the galaxy, it gets slowed down because it's taking a longer path. And so what it does is it will take the two paths that sort of are the most efficient ones. This is how gravitational lensing works. Okay, so here's how it looks like in real life. This top left one is the very first gravitational lens that was discovered. Oops, oh no. I'm really bad at this thing. So here's the first lens discovered. There's a galaxy here, sort of hard to see. That's the massive object that's bending the light, and we see two images of a quasar on either side of that galaxy. A quasar is a less spectacular version of the blazar that Victoria was telling us about in the break. Okay, so these are the three most common types of gravitational lenses we see. There's two images, like the first one. Here's one with 4 images. So these things labeled A, B, C, and D are 4 images of a background quasar. The lensing galaxy is here in the middle. And here's something called an Einstein ring. And essentially there is perfect alignment between the galaxy, the background object, and you. And so every path around the galaxy gets bent in exactly the right way for you to see the background object. And so you see a little bullseye pattern where the thing in the background is the galaxy that's having its light bent, and the thing in the foreground is the galaxy that's bending the light. Okay, on the bottom are my 2 favorite gravitational lenses because I helped discover them. Okay, so here is a great everyday example of a gravitational lens. You may have seen this in a previous Astronomy on Tap talk. I don't know. If you haven't, here it is. It turns out that gravity bends light in exactly the same way that glass can bend light. You just need glass to have the right shape. And it turns out that a wine glass, a stemmed wine glass, actually has essentially the right shape to represent the gravitational lens. Okay, because I'm klutzy, I have stemless glassware, so I can't do this at home. But if you want to impress people at parties, you can show them gravitational lensing analogies with your wine glass. So here we have the bottom right one has 2 images of the background object, which is the candle. The top right one has 4 images. You can't really see the 4th one, but 1, 2, 3, 4. And the bottom left one is an Einstein ring. I will say that if you want to impress people at parties, it helps if the wine glass is empty before you start doing this. I've learned this from experience. Okay, so how do we use this lensing to detect subhalos? So here's the basic idea. If you get this, you get what I do for my research. So here we have an Einstein ring that's produced by the wine glass. Now imagine, so the properties of the wine glass will set sort of the diameter of this ring and its properties. But imagine that the wine glass has imperfections in it, little bubbles, little specks of other things. What that can do is distort the image of the wine glass, okay, of the ring. And so you'll get little wiggles in that pattern due to the imperfections in the glass. The same thing happens in gravitational lensing, is that if you have not a smooth dark matter halo, but a clumpy one, like all the models say we should have, then you get wiggles in the lensed images. And here is a great example of this happening in real life. So here, the thing that's bending the light is a galaxy group. So it's a bunch of galaxies that are held together by their own gravity. That's in the center. This blue long arc here and this little blue short thing on the other side, this is light from a single galaxy that's having its light bent and distorted by the gravitational lens. And if you're paying a lot of attention, you see there's something odd going on down there. And if I zoom in on that, what you see is that there's a little yellow blob there, which is another galaxy that's living in the group. So this is the subhalo, is clumpy. But the other thing is, what you see is this blue arc comes down, there's a break, it splits, it curves around, and then it goes on. Okay, why is this important? This is important because that signature would be there. We would be able to tell that there was some kind of extra mass there, even if we could not see that yellow blob, just based on what that blue light is doing. So the fact that the blue arc comes down, it breaks up, it splits, it curves around, is only responding to the mass of that object. It does not require us to see that yellow blob to know what that object is. And we can not only see that the object is there, but the amount of splitting of the light tells us the mass of the object. So this is exactly what we need to do our studies about dark matter. So here's the thing. I have terrible vision. So if I were to look back at this wine glass and I said there's imperfections in that wine glass that's causing wiggles in it, and I take my glasses off, I can't see a damn thing. Excuse my language. So you need to be able to see this in great detail to see the little wiggles that are introduced by this. And if we're talking about a single galaxy and its subhalos rather than a group of galaxies, the splitting that you see is very, very small. And that means that you have to have very, very sharp vision to see this. And that brings me to part 3 of the talk. Oops. Which is how we see this. So how do we get super sharp vision of our gravitational lens systems? So it turns out that the Earth's atmosphere is terrible for astronomers. Okay, because the Earth's atmosphere has a lot of turbulence in it, and if you're looking at light, at least in the optical light that we can see with what we can detect with our eyes, all this turbulence and wind in the atmosphere blurs everything out and makes it like it is if I take my glasses off. Bad. Okay, I will concede that having an atmosphere has its benefits, but as an astronomer, not great. So there's some things that we can do about this. We can spend billions of dollars to launch a mirror into space, and that's what the Hubble Space Telescope is. And the Hubble Space Telescope gives us great pictures of the sky. The other thing is you can invest in a lot of interesting technology that can try to take out this blurring effect of the atmosphere. This is a technique called adaptive optics, or I'll say AO here, and this works with big telescopes on the ground. Okay, before I get to the third point there, I will say, so in astronomy, if you had no atmosphere to worry about, the bigger your telescope is, the sharper the image is, okay? And so the Hubble Space Telescope is fantastic, but it's 2.5 meters across. The telescope that I use for most of my research is the Keck telescope, which is this thing here, which is 10 meters across. So if we didn't have to worry about the atmosphere, the Keck telescope, even though it's here on the ground, should give you sharper images than the Hubble Space Telescope. Okay, and so we use adaptive optics, and we actually see this as the case. And one of the really cool things about using adaptive optics with the Keck telescope is you get to use a honking big laser that you shoot up into the sky. Okay, and what do I mean by honking big? Okay, so I don't know, because this, as you can probably tell, is not my usual laser pointer, which is why I'm having so much trouble with it. But usually these things are several tens of milliwatts, like 50 milliwatts. The laser that you see coming up from Keck in this picture here is 10 to 15 watts. So it's almost 1,000 times brighter than this laser, which is, they say, do not point at people's eyes, and for which you can get arrested if you point it at airplanes. So they're shooting a really powerful laser up in the sky. You use the fake star that laser creates high up in the atmosphere to do this adaptive optics, and here's what it can look like in an ideal case. So I've shown you 3 pictures that I've taken of the same object down the bottom. The first one is a picture that I took with Keck telescope with no adaptive optics. This is what it looks like, just some blob. You put a $1.5 billion telescope up in the in space, the Hubble Space Telescope, and this is what it looks like. And for this object with Keck with adaptive optics, it looks like that, much better. Okay, this is physics in action. Science works. Okay, great. And so for some objects at least, the Keck telescopes here on the ground, which only cost something like $75 million to build as opposed to 1.5 billion, are better. So this adaptive optics is now essentially every big telescope is now using it. This picture down at the very bottom, which I also used for my slide, shows 3 adaptive optics systems on the summit of Mauna Kea being used at the same time. So here are the 2 Keck telescopes. One laser is going off this way, one laser is going off this way. Here's the Subaru telescope, which is the Japanese telescope, and it's shooting its laser off it also. So that's kind of cool stuff. All right, so where are we now? Here I'm showing you actual data from my research. So we've looked at a whole bunch of gravitational lenses. These are pictures that we took with the Keck telescope. We can find subhalos. I'm not going to explain this, but this little blob here is actually a detection that we made of a subhalo in a very, very distant galaxy. And essentially what we're doing is we're going to apply this analysis to all of these lenses, and we're going to compare what we find to what the predictions are from these models of the cold dark matter and the warm dark matter. And so my hope is that in several years' time, I could give an Astronomy on Tap talk and actually tell you whether cold dark matter works or whether we have to use some other model of dark matter. Thank you.
I want to play your video that didn't work. It's beautiful, right? Ooh.
Okay, thanks to Chris, who was a wonderful talk. First question, is there dark matter inside humans?
There may very well be. Although the density of dark matter where we are is not super high, so unlike the neutrinos, probably not as much. I don't actually know the answer to this question.
I think it's yes.
Yeah.
How can you measure the temperature of dark matter?
How do you measure? So essentially, the idea is that I'm going to be sort of physicsy here. The temperature that when we talk about warm dark matter and cold dark matter, is essentially how fast the particles are moving. And so the idea is that if the temperature is too high, then the dark matter particles are moving too fast to be held by the gravity of these little blobs, and you won't see the little blobs because all the dark matter escapes. If they're moving too slow, then they can be held by the gravity, and you actually see the blobs. And so this is actually the whole, what I'm trying to do is try to count how many blobs we see. The more blobs we see, the colder the dark matter is, the slower the particles are moving, because it tells us that they cannot escape from the gravity of their little blobs.
Okay, next question is the wine glass analogy a coincidence or a pattern of nature?
Is it coincidence or a what?
Pattern of nature?
Pattern of nature. It's essentially, well, the fact that it's a wine glass is maybe a coincidence, but no, I think, so when I was in graduate school, I could have showed you a different version of this slide. When I was in graduate school, my supervisor went to a glass blowing shop, I guess, and paid a lot of money to have a piece of glass engineered that would have the same characteristics of the gravitational lens. And I looked at that, and as a poor grad student, said, I'll never be able to do that, to be able to afford something like that. And essentially what you need is a piece of glass that's thicker in the middle and thinner on the sides. And it was my friend Phil Marshall who realized that the bottom of a wine glass has essentially that shape. And I like it because since we're in very close to wine country, and since I drink a whole lot of wine, it's a really nice analogy.
Thank you.
Sorry.
Okay, so it's time to see who win the raffle, and So the name is Robert.
Is Robert still here? Yeah, this is Robert. Robert's been here since the first Astronomy on Tap. So congrats to Robert. Thank you for coming. Yeah. Thank you guys all for coming.
Okay.
Okay, so again,
So
I'm gonna-
what Robert win with the, I don't remember,
What?
the cup, no?
Okay, so the winner of the raffle is 403051, and this person has written the name on the back of the ticket, and it's Sarah Loebman. So congratulations, Sarah Loebman, on winning the raffle.
I know the name. Sarah actually was the first speaker on the first Astronomy
Yeah,
on Tap.
Sarah
So
was here. She talked about.
I think
the
she
moon.
deserves it.
Yeah, she definitely deserves it. Okay, thank you guys so much for coming. We'll be back in October. Yeah, thank you.